Okay, so good morning, all of you. So, in the previous session, we discussed that series RL circuit and one or 2 points about the series RC circuit. And today, we will try to discuss the further part of the series RC circuit. Once again, all of you, please just concentrate towards the circuit diagram. The circuit diagram for the series RC circuit, it means a pure resistor and the pure capacitor are connected in series, and this series combination is connected across an alternating voltage source. So this capital V represents the RMS value of a voltage source, and this is the 50 Hz frequency. Due to this alternating voltage source, the alternating current, it flows through the circuit. And as you know that the basic properties of the series circuit, the current flowing through each component is the same, means current through R and the current through C is the same. So this capital I in this diagram represents the RMS value of a current. When the current will flow through both the components according to Ohm's law, the voltage is developed. So the RMS value of voltage across R, it can be represented by VR, and which is nothing but I into R. And that RMS value of a voltage across the capacitor, it is nothing but the V to the base C, and we can write that formula for VC, which is equal to I into XC, where XC is known as a capacitive reactance, which is equal to 1 upon omega C, which is equal to 1 upon 2 pi XC. Now the second part is the phasor diagram. The one rule I have already given to you, and that is nothing but when you want to draw the phasor diagram for series circuit, we always consider that current phase as a reference phase. Now with the help of this reference phase, we can draw the phasor for VR and VC. As we know that the relation in between VR and I, that is nothing but they are in same phase. So that VR is also in same phase with the I. And the relation in between VC and I, that is nothing but, give me 1 minute. Hello sir. हाँ sir. But मग कसं करू दे मी तुमचं लेक्चर. Am I audible?
Yes, sir.
Yes, sir.
Okay. So the relation in between that VC and I is nothing but the current lead the voltage by 90 degrees. So that VC is towards the downward direction. And the total voltage V is the phasor addition of VR and VC. So that when I make the parallelogram, the hypotenuse of this parallelogram will represent that the capital V. And that angle between the voltage and current, it's a phi. And from this phasor diagram, one thing it is clear, the current will lead the voltage by an angle phi. So that equation for the current I is Im sine omega t plus phi. Now the third part of this derivation is the voltage triangle. Once again, we consider the same triangle with the horizontal line represent that VR, vertical line represent that VC, and that hypotenuse will represent that V. So according to this triangle, we can write that formula for applied voltage. V is equal to under root of VR square plus VC square. Okay, so that V is equal to under root of IR square plus IXC square. So this total voltage V, which is equal to under root of VR square plus VC square. What is mean by this VR? VR is nothing but I into R, and VC is nothing but I into XC. So that when I take that item common, so here we got that formula for impedance, which is Z is equal to under root of R square plus XC square. So that my formula for applied voltage V is equal to I into J. Up to this point, is there any doubt? Yes or no?
No, sir.
Okay. After that, you can also write that formula for power factor. What is mean by that power factor? Which is nothing but the cos of angle between voltage and current. Now see that voltage triangle and give me that. What is that? How you can calculate that cos phi? That is nothing but VR upon V. But VR means what? Which is nothing but I into R. And V is nothing but what? Which is nothing but I into J. Now you can observe here the formula for power factor is always remain same, and that is nothing but cos phi is equal to R upon Z. Get it, my point? So this is the thing is there. Now the fourth part in this derivation, which is nothing but impedance triangle. Now once again, I just consider the same triangle here. See that? As this horizontal line represents that VR, and in that the opposing part to the current, which is nothing but R. So this side represents that R. Vertical line represents that VC, in that the opposing part to the flow of current, which is nothing but XC. And that hypotenuse will represent that V, this one, according to this formula, the opposing part to the flow of current, which is nothing but J, and this is the phase angle phi as it is. And once again, with the help of this impedance triangle, we can derive the same formula, which is nothing but Z is equal to under root of R square plus XC square. Okay, then you can calculate that power factor. Cos phi is equal to R upon Z. Then you can also calculate that phase angle phi, which is equal to tan inverse of XC upon R. And now if I want to write this impedance for series RC circuit in a rectangular form, how you can write it down in a rectangular form? So as you know that for the rectangular form, if I want to write that Z in a rectangular form, we may require its X component and the Y component. But if you observe here, the X component of the Z is a, I say that if I try to make that with a dotted line, this X component of this Z is nothing but R. So that X component is R, and the Y component is XC, but as it is in a downward direction, so that it's a symbol or the sign for XC is a minus sign. So that I can write impedance Z, which is equal to R minus JXC. So what you have to concentrate here, whenever the impedance is written in a rectangular form, so your focus is towards that sign. Now here that minus sign, it indicates that this is the impedance of capacitive circuit. It means that when it is written Z is equal to 10 minus J 20. So now you can compare this equation with this box. This 10 will represent that value of R, and this 20, as it is the minus sign, so that it is represented by that XC, because that minus sign indicates the capacitive circuit. If you observe that the impedance in a series RL circuit, then you can observe that in the series RL circuit, the impedance equation, it comes with the positive sign. Is it right? And as we say that, or we will note the thing here, when the impedance it comes in the positive sign, then it is, we call it a series RL circuit. And when that impedance, when it is written in rectangular form with a negative sign, it simply represents negative, means R minus jX. If it is in this format, then we say that this is the impedance of series RC circuit is there. Okay, so it's my request to you, please take the screenshot of it. Taken?
Yes, sir.
Okay. And then after that, the fifth part, once again, which is nothing but we have to write the formula for power. Now see that before proceed further, first we have to write the formula for instantaneous power. How we can write that instantaneous power? This instantaneous power P, which is equal to instantaneous voltage into instantaneous current. Now for pure capacitive circuit or for series RC circuit, the voltage equation is Vm sine omega t, and for series RC circuit, that equation for current, it becomes Im sine in bracket omega t minus phi. These are the two equations. This is the equation for instantaneous voltage, and this is the equation for the instantaneous current. So we can write here P is equal to Vm Im sine omega t into sine in bracket omega t minus phi. Okay. Also, I can also write like that, P is equal to Vm Im 2 sine omega t into sine omega t minus phi. Okay. It's a minus pi or a plus pi here? It's a plus pi is there because it's a capacitive circuit is there. It's my mistake. Let me correct it. So this is nothing but, let me correct it. In the capacitive circuit, the current will lead that voltage. So it's a plus pi, and I can write it down upon 2. Okay, because this formula we know that 2 sine A sine B. So that I just make it like that. And then if I want to calculate that the total power or the average power over a one complete cycle, then as per that our normal formula, integration of 0 to 2 pi, the instantaneous power Vm Im upon 2 in bracket I can write 2 sine omega t into sine in bracket omega t minus pi into d omega t upon the base is 2 pi. So when I try to solve this integration, then here you will get it. Yes,
sir, omega t plus phi.
yes, please.
Sir,
Okay.
omega t.
Yes. Still I did the mistake here. Very good. Thank you, please. So I can take that constant term outside. Vm Im upon, now this 2 into 2, it becomes 4 pi. Okay. And now in this integration, I will try to convert this 2 sine A sine B, which is nothing but in bracket cos A minus B, so that omega t minus pi. So directly can I write it down? It's a cos of minus pi. Is it okay to you? Minus cos of A plus B, which is nothing but 2 omega t plus phi into d omega t. And now if I take that individual integration here, Vm Im upon 4 pi Now in bracket I can take integration of 0 to 2 pi cos phi into d omega t minus integration of 0 to 2 pi cos of 2 omega t plus phi into d omega t. This is in one bracket. So if you calculate the integration of this second term, it's a sine 2 pi, and sine 0 and sine 2 pi, it's a 0. So this second term is always equal to 0. So only the first term it remains, and in that I can write Vm Im upon 4 pi. Cos phi is a constant, so let me take it outside, cos pi, and in bracket what it remains, it's a omega t, and the limit should be 0 to 2 pi. Is it right? And when I substitute that limit, then here we got it Vm Im upon 4 pi cos phi, in bracket I say that 2 pi minus 0, so that the final thing we got it here, which is nothing but Vm Im upon 2 cos phi. And these things I can write Vm upon root 2 Im upon root 2 into cos phi, so that my formula for the total power, it becomes Vi cos phi. And if you observe that the same formula we get it in a series RL circuit also, that is nothing but Vi cos pi, so that this formula is a unique for the AC circuit. Whenever you want to calculate that power in that AC circuit, we always use that formula. DC circuit मध्ये आपण काय फॉर्म्युला यूज करत होतो, P is equal to VI, परंतु AC circuit मध्ये आपण काय यूज करणार आहे फॉर्म्युला, P is equal to VI cos phi is there. So it's my request to you all, please take the screenshot of it. Take it. घेतला का?
Yes.
Okay. So this is about
Yes, sir.
RC circuit. Okay. And now the next derivation, which is nothing but series RLC circuit. And now see that this series RLC circuit is so simple, because we have already learned the pure R, pure L, pure C, then series RL, series RC, and now it becomes series RLC circuit. So all the concepts, when you merge in this circuit, then we call it a series RL circuit here. Now let me try to draw that, the first part, which is nothing but the circuit diagram. As you know that we have to consider all these three components. So let me consider that pure R, pure L, and pure C, and they are connected across an alternating voltage source. Okay, so this is a R, this is a L, this is a C, and this is the RMS value of a applied voltage with the frequency 50 Hertz. So due to this alternating voltage, alternating current it flows, and that RMS value of alternating current, let me represent with this capital I. Okay, so due to this I, when it flows through this RLC, it will develop the alternating voltage. So let me consider that RMS value of voltage across that R is a VR, RMS value of voltage across L is a VL, and RMS value of voltage across C is a VC. And based on that, we can write that formula for RMS value of voltage across R VR, which is nothing but I into R. RMS value of voltage across L, which is nothing but VL, which is nothing but I into XL, where XL which is equal to omega L, which is equal to 2 pi FL. And the RMS value of voltage across capacitor, it can represent with the VC, which is nothing but I into XC, and that to be calculated, or that where XC is equal to 1 upon omega C, which is equal to 1 upon 2 pi FC. Is it right? So this is about the circuit diagram. And then, as we know that in this circuit, the three components are used, but out of these three components, the L and C are called as a reactive component. Why we call it a reactive component? Because as we know that these two components will not consume the power. Only the R will consume the power. But these L and C will take the power from source, but it will return back to the source is there. That's why this L and C, we call it a reactive component. And based on the value of VL and the VC, this circuit series RLC will classified into three types, or it has its three cases. So what are these three cases? So let's we consider that case number one. As I said that based on that value of VL and VC, the RLC will classified in three cases. If you consider that VL is greater than VC, or XL is greater than XC, then these types of circuit is called as an inductive circuit. Why we say that it's an inductive circuit? Because VL is greater than VC, or XL is greater than VL is greater. आता VL कधी ग्रेटर असू शकतो? I तर सेम आहे, म्हणजे जर XL ची व्हॅल्यू जर मोठी असेल तर डेफिनेटली VL हा मोठा असणार आहे VC पेक्षा. So this is the first case. Second case is that exactly reverse. If VL is less than VC, or XL is less than XC, then this type of circuit is known as capacitive circuit. Capacitive circuit. And now the third case is that, as I say that, when these two, when VL, when it is equal to VC, or XL is equal to XC, then this types of circuit is acts as pure resistive circuit. Okay. So now based on these three cases, we have to discuss the series RLC circuit here. Okay. So please take the screenshot of it. Take it.
Yes, sir.
Okay. Now let's we try to discuss that case number one, which is nothing but VL is greater than VC. So here I will consider that case number one. Here I can write case 1, which is VL greater than VC, or XL greater than XC. That time we know that circuit will act as a inductive circuit. Inductive circuit. Now let's see the phasor diagram. Phasor diagram for this case. Now how to draw that phasor diagram for this case? Please see that. The rule, you know that whenever you want to draw the phasor diagram for series circuit, we always consider that current phase as a reference phase. So this is the current phase. Now VR is always in phase with I. So this is represented by VR. Now how you can represent that VL and the I, the relation is current is lagging, so that I need to show the VL along upward direction. So this will represent that VL, so that current will lag anti-clockwise direction, in an anti-clockwise direction by 90 degrees. And as we consider that VL is greater, so how much is the length you consider to draw that VL phasor? Now, as we want to draw that VC, and how I can draw that VC? In a downward direction, but the length of the phasor of VC is less than the length of a VL. You can see here, because we consider that the case is VL is greater than VC. And now if you observe that the VL and VC are opposite to one another, so that the when I want to show that applied voltage, let me consider this point, and this point is nothing but the subtraction of these two phasor, that is nothing but VL minus VC, as they are opposite to one another. And now in between this 0 point to this point will represent the VL minus VC. And now when I make that parallelogram here, then the hypotenuse of this parallelogram will represent the total voltage V, and that angle between the voltage and current will is nothing but the phi. Is it nothing but that phi? Okay, get it my point? Now the second case is that case number 2. Let me complete these things. Here I can write case number 2. Okay, and the case number 2 is VL is less than VC, or XL is less than XC, and that time we say that this circuit will act as a capacitive circuit. Okay, and now see that what is the phasor diagram for it. Phasor diagram, this is very important to understand the further concept. Let me assume that the current phase as a reference phase. Suppose this is the current phase. How I can draw the VR? VR is always along with that I. So this is that VR. Then VL, as we consider that VL is a small and the VC is greater. So let me consider that very small line for to represent that VL. It will represent that VL. And now I consider that the bigger line for VC. This is the VC here. Now try to find the difference between them. And now this point, or means I say that from 0 to this length will represent VC minus VL. Get it my point? And now if I make the parallelogram in between these 2 points, then the hypotenuse of this parallelogram will represent the total voltage, and that angle between the voltage and current, this is nothing but phi. Now have you noticed that if you see that the case number 1, what is the relation in between voltage and current? And if you see that the case number 2, what is the relation in between voltage and current? Can you notice the difference here? Yes or no? If you see that the case number 1, can I say that in the case first, current is a lagging behind by the voltage by an angle phi? And when the current it will lag, so we say that it is the inductive circuit, because in inductive circuit current is lagging. And if you see that the phasor diagram for the second case, you can say that the current will lead the applied voltage by an angle phi, so that it is acts as a capacitive circuit. Have you noticed this difference here? Yes or no? Give me response.
Yes, sir.
Okay. And now based on this, both this phasor diagram, we can draw that the voltage triangle. See that voltage triangle. Now here I can try to draw that the voltage triangle for the first case. This is the voltage triangle. This side represents that VR. This side represents that VL minus VC. This side represents that V, and this is the phase angle phi. If I try to draw that voltage triangle for the second case, what is that voltage triangle? Just see that this is the voltage triangle in this way. Okay, so this side represents that VR, this side represents that VC minus VL, and this side represents that V. This is the phase angle phi. And from that, we can write that equation. I can write that equation for applied voltage, RMS value of applied voltage, which is equal to under root of VR square plus in bracket VL minus VC square. And as we know that the formula for VR, VL and VC, let me try to put these formulae here. So I can write in bracket I into R square plus in bracket I XL minus I XC bracket square. So when I take that I term common, then what is the remaining part, which is in under root, which is nothing but R square plus in bracket XL minus XC square, where this denominator, under root part will represent the Z, which is nothing but under root of R square plus in bracket XL minus XC square. Okay, so that my formula for total voltage, it becomes I into Z. Okay, similarly, if I write the formula for the total voltage in this case number second, then this formula, it becomes V is equal to under root of VR square plus, now here the case is VC minus VL square. मग आता या ठिकाणी जर आपण न्यूमेरिकल सॉल्व करताना चुकून VL मायनस VC स्क्वेअर केलं तर या टोटल व्होल्टेजच्या व्हॅल्यू मध्ये फरक पडेल का?
नाही
पडणार, कारण का तर त्यांच्या डिफरन्सचा स्क्वेअर आहे आणि डिफरन्सचा स्क्वेअर असल्यामुळे या व्हॅल्यू मध्ये फरक पडणार नाही. त्यामुळे न्यूमेरिकल सॉल्व करताना जरी थोडस चूक झाली VL मायनस VC किंवा VC मायनस VL, then also no problem at all. Okay, then let me try to put that the value here, and that is nothing but I R it's a square plus VC is nothing but I XC minus I XL bracket square. So when I take that I term common, then it becomes I under root of what is remaining terms, R square plus in bracket XC minus XL, it's a square. So that in this second case, we have that the formula for Z, which is equal to under root of R square plus in bracket XC minus XL bracket square. आता जरी झेडच्या फॉर्म्युलेमध्ये या सेकंड केस मध्ये न्यूमेरिकल सॉल्व करताना चुकून XL मायनस XC ब्रॅकेट स्क्वेअर झालं तरी देखील या झेडच्या व्हॅल्यू मध्ये फरक पडणार नाही. सो डोंट वरी अबाउट इट. अँड देन दिस फॉर्म्युला फॉर अप्लाइड व्होल्टेज इज ऑलवेज रिमेन सेम, which is nothing but V is equal to I into Z. Is it that clear? Please take the screenshot of it. Have you taken? Yes or no?
Yes, sir.
Yes, sir.
Okay. Now, the second part is that, once again, I will make that the two column. One is here I can write case first, and here I can write case second. Now if you try to remember that, the impedance triangle, so the triangle, it should be like this. For the case first, as VL greater than VC, so this is VR. Oh, sorry. Now impedance, for the impedance triangle, I need to replace VR with the R. This is XL minus XC. This is Z. This is phase angle phi. And now the case second is VL less than VC. So in terms of this case second, how I can draw that impedance triangle? The triangle, it's remains same, and that is nothing but this one. So here I can represent, I say that R, this is XC minus XL, and this is Z, this is the phase angle phi. So from this triangle also, we can write Z is equal to under root of R square plus in bracket XL minus XC bracket square. In this case, I can write Z is equal to under root of R square plus XC minus XL bracket square. Again, if I want to write that formula for power factor, which is nothing but cos phi, and that formula is always remain same. Case may be anything, circuit may be anything. The formula for the power factor in a AC circuit is always same, and that is nothing but cos phi is equal to R by Z. Now in this case also, if you try to calculate that power factor, which is always remain same, that is nothing but R by Z. Now if you calculate that phase angle phi, then you can calculate with the help of tan inverse XL minus XC upon R, and here the formula for phi, which is equal to tan inverse XC minus XL upon R is there. Get it my point? And once again I will repeat the thing here. The formula for power, the case may be anything, circuit may be anything, the formula for the power is always remain same, which is nothing but VI cos phi. This is the active power, which it has its a unit as a watt, and the formula for power, which is also here in this case VI cos phi, and its a unit is watt. Before that, have I explained that the three different types of power: active power, reactive power, and the apparent power? Yes or no?
No, sir.
Okay. So please take a screenshot of it so that I can try to explain. Take it.
Yes.
Okay. And now the third case, only these two cases are over. Now try to consider that the third case. Third case is when VL is equal to VC. Let me consider that third case here. Case third, I say that VL, which is equal to VC, or XL, which is equal to XC, and this case it acts like a pure resistive circuit. How it acts like a pure resistive circuit? Let me try to show it. Let's we try to draw the Phasor diagram first. Phasor diagram. Now see that what is that Phasor diagram? As we consider that VL and VC are same, so before that let me consider that the current phase. Now VR is always in phase with that current, so this is that VR, and then the length of a VL and the length of a VC are remain same. In this way I try to draw the VL and VC. So this is the VC, this is that VL according to the concept, and these two lengths are remain same, means these two, if I try to do the subtraction, so these two will get cancelled, And as these two lengths will get cancelled, we cannot draw the triangle in the third case. Get it my point? And then also, when I want to draw, or when I try to write the formula for the total voltage, RMS value of total voltage, as you know that our regular formula for the total voltage, which is nothing but VR square plus, in bracket, either you can write VL minus VC, or you can write VC minus VL. But what is that value of these things? As we consider that VL is equal to VC, so may I say that the difference is 0? Is it right? So what it remains? The total voltage, which is equal to under root of VR square, and that is nothing but V is equal to VR. This is the important thing. That's why we say that this circuit, it acts as a pure resistive circuit, because total voltage is equal to the voltage drop across the resistor here. Is it that clear? And that another important point is that as it acts as a pure resistive circuit, it means that the total voltage is nothing but the VR. So can I say that this phasor is also represents the total voltage here? So can you give me that what is the phase angle between the total voltage and total current? Yes, what is that phase angle?
0.
It's a 0 degree. So can you give me that the power factor of this circuit, cos phi, which is equal to cos 0, which is equal to 1. Now, if I want to calculate that power in this case, P, as we have that formula VI cos phi, so can I say that where cos phi is equal to 1, so that P is equal to V into I, and हे derivation तुम्हाला pure resistive circuit मध्ये मिळालं होतं बघा. And as we say that this XL is equal to XC, so what is that impedance in this case? Z is equal to, जरी आपण तो फॉर्म्युला लिहिला अंडर रूट ऑफ R स्क्वेअर प्लस XL minus XC लिहा किंवा XC minus XL लिहा, but this term is going to be 0. So can I say that Z is equal to under root of R square, so that Z is equal to R? That's why we say that this circuit, it acts like a pure resistive circuit. Is it that clear? Please take a screenshot of it. घेतला का?
Yes, sir.
Okay. And now, once again, one important thing I want to discuss here in this third case, and that is nothing but, as we know that where we say that this third case, when XL is equal to XC, and this condition is called as a resonance condition. What we call it a resonance condition. Why it is called as a resonance condition? Because as we know that inductive reactance, it is represented with XL. What is mean by this XL? So as we know that XL, which is equal to omega L, which is equal to 2 pi FL. So may I say here, XL is directly proportional to the frequency. Is it right? And the second part is capacitive reactance. Capacitive reactance, which is nothing but XC, where XC is equal to 1 upon omega C, which is equal to 1 upon 2 pi FC. So may I say here, XC is inversely proportional to the frequency. And when XL is equal to XC, it means that at one particular frequency, these two components are equal, and that frequency is called as resonant frequency. What we call? It's a resonant frequency. Now, how I draw that graph here? Suppose if I try to draw the graph, see here, frequency versus X component. As we know that XL is directly proportional to the frequency, so its a graph is like this. This is the XL, which is a straight line because it is directly proportional. And when I want to draw the graph for that XC, which is, oh sorry, here I did that mistake. It's a reciprocal 1 upon frequency, so that if I want to draw the graph for that XC, so it should be like this. So this is that XC here. And this is the meeting point. This is the common point in between these two graphs, where at this point XL is equal to XC, and this is known as resonant frequency. When these two values are equal, we call it a resonant frequency. And what is that formula for resonant frequency? How you can calculate it? As we know that at this resonant point, XL, which is equal to XC. What is mean by XL? Which is nothing but 2 pi FR. आता मी तिथं F लिहित नाही, कारण हे जे दोन कंपोनंट ज्यावेळेस इक्वल आहेत, म्हणजे त्यावेळेस जी फ्रिक्वेन्सी आहे त्याला म्हटलं जातं रेझोनंट फ्रिक्वेन्सी, and it is represented with FR into L, 2 pi FL, and XC is nothing but 1 upon 2 pi FRC. When I transfer this FR to left hand side, then it comes like that, FR square, and the remaining terms at other side, so it will becomes like 2 pi, it's a square LC. Is it right? So that we have that formula for the resonant frequency FR, which is equal to 1 upon 2 pi under root of LC. This is the formula for resonant frequency. Maybe this formula, it may ask for MCQ type of question. Is it that clear? Please take a screenshot of it. Taken?
Yes, sir.
Yes, sir.
And so here I declare that this is our third unit, AC circuit and the single phase transformer. It's completely over AC circuit, single phase AC circuit. It's completely over. Now I will give that the few assignment question, but I will use that another 1 hour session just to solve the few numericals, at least 1 or 2 numerical, because as you know that exam is only MCQ type, so definitely I will not use that more focus on that numerical part, but I will use that the next 1 hour just to solve the numerical on it. So it's my request to you all for the next session